Great. Well, welcome everyone, and thanks for joining us today. I'm Jodie Goodall. I'm the Head of Organisational Reliability here at Brady Hayward in Australia. Today I'm your host for the session, which is focusing on the key considerations for legal teams who are briefing technical experts in construction disputes. It's presented by Dr. Sean Brady, and it was so popular last time. This is the second session we've put on, so it's great to have you. I'm delighted to introduce you to our presenter today, Dr. Sean Brady. Sean has acted as an expert witness in numerous proceedings involving a range of constructed facilities. He's a chartered professional engineer, a fellow of Engineers Australia, a director of the Society of Construction Law Australia, and a member of the Singapore International Mediation Centre's panel of experts. Sean also speaks, podcasts, and writes on the subjects of failure, human behaviour, data analytics, and engineering disasters. And I'll tell you a bit more about that later. So welcome, Sean, and thanks for joining us.
Hello, everyone. Thank you for joining us for today's webinar. I'm just going to share my screen so we can kick off. This is all about briefing engineering experts in construction disputes. I've done this webinar quite a few times over the years, and I think it's interesting because it still seems quite fresh, because the problems the legal community has with briefing experts don't seem to have changed too much in the last 10 years since I started doing this. There's a whole range of problems we could talk about in briefing engineering experts. Engineers do think differently. We will talk about that. Engineers tend to communicate visually as opposed to with the written word, which the legal community tends to prefer writing. So there's lots of issues we could talk about, but the key issue I really want to talk about is the difference between forensics and design. I think if you understand that and you ask yourself a couple of key questions before engaging an expert, it just makes the whole process a lot smoother and a lot easier to understand why things sometimes don't go right. And if we start with sort of the key questions here, I think, when something goes wrong, and let's stick with engineering failures and let's stick with structural failures because I'm a structural engineer by training, but pretty much everything I'm going to say applies to all forms of engineering. But when something goes wrong, there's usually the first question is what caused the failure? And the second question is, well, did someone do something wrong? Was the structure or engineering product designed and constructed properly in the first place? Now, I think when you put these two questions together, if you're a lawyer, it makes really good sense that these are two separate questions. But unfortunately for us engineers, we don't always read them as two separate questions. And that's where a lot of the confusion comes from. Because, of course, the first question is really the causation question. And the second question is the compliance question. Did people do what they were meant to do? And we'll keep those fairly broad for a moment. Let's stick with the causation piece first, because I think this is where a lot of the issues come from. And what we'll do is we'll take a case study and we'll look at what I believe is a pretty good causation investigation. So we'll jump straight in. We'll go to Boston in the post-war years. And Boston was struggling with the same issues as every US city was struggling with, which was, the explosion in motor car use. How do you get these vehicles traveling through your heavily congested cities? Boston came up with a novel idea. If you have a look at the photographs, you'll see the novel idea. They put in elevated roadways. Let's get the traffic up off the street, up into the air, away from pedestrians, and that'll solve all the problems. They even had a fancy name for it. They called it the highways in the sky. But the reality of it was stunningly different. It became known as the Green Monster very, very quickly. It never really worked. It got congested really quickly, almost from the beginning. And if you think about this, you've got this green monster in the middle of your city, in your prime real estate areas. It's causing pollution, it's noisy. There's a whole range of issues with it, and there's a whole range of reasons why you want to get rid of this thing. And what happened was Boston lobbied the federal government for decades to get money to get rid of this infrastructure. And eventually they were successful, and they set out on a massive project. It was the biggest public infrastructure project undertaken in the US. It was $14 billion, and it was going to run for 20 years. It had a fancy name, but very quickly it became known as just the Big Dig. And it was all about taking that elevated walkway array. They went and built 200 bridges. They put in kilometers of tunnel, and they slowly opened up this new infrastructure over this 20-year period. This is the I-90 connector tunnel. So this was opened in 2000, finished construction in 1999, opened in 2000, and it performed without any major issues for 6 years until we come to the 10th of July 2006. It's 11 o'clock at night and they have a massive failure. What you're looking at here is you're looking at concrete ceiling panels that were connected onto the roof of the tunnel and they have collapsed onto the roadway below. It's a deceptive photograph. You're actually looking at 24 ton of rubble on that floor. So this is incredibly heavy. If you look carefully under the back panel, you'll see a white number plate of a car. It was a freak accident that the car was there at the time. Husband and wife in the car. The wife was killed instantly and the husband got out with cuts and bruises. So this was a pretty catastrophic failure in a major piece of infrastructure. So what I want you to imagine if you're a lawyer is that you are dispatching and engaging and sending out some engineers to do an investigation, a causation investigation of what happened in this tunnel. And what we'll do is we'll step through the National Transportation Safety Board's investigation, so they're shortened to the NTSB, and we'll look at what they did, because it's a really good example of what a good quality investigation looks like. Before we do that, we need to do a little bit of engineering, and I'll try and be as gentle as I can. This is the way the tunnel was meant to work. You have a ceiling in the tunnel. That ceiling space is quite large. It's there for ventilation purposes. You've also got other services in there as well. And what they do is they complete the tunnel and they want to have this ceiling space with these ceiling panels. So we've got two sets of panels we're interested here. The end panels, which are closest to the wall, which are the northern panels, and the center panels known as the C panels, which run down the center of the roadway. Now these concrete panels are held up in place using support rods. So you've got the N1, the M1, and the M2. They're held up by support beams. Those support beams then in turn are held up by support rods, diagonal and vertical rods. The rods are then connected to hanger plates, which are just flat plates with a bolt hole in them. And then they are epoxy anchored into the roof. So that's the way the structural system works. Panels supported by beams supported by rods connected to plates epoxy anchored into the roof of the tunnel. Now, what does an epoxy anchor really mean? Well, that's it there in the photo. What happens is the contractor comes along, they drill a hole in the roof, they clean out that hole really, really carefully, and there's very set procedures on how you do that. Then you push an epoxy up into that hole and you push a threaded rod up into the hole after that. The epoxy sits and now you've got a permanent anchor place in the roof. And what you can do is you can take your hanger plate, which you can see there in the picture, and you can just put a nut on the end of that anchor rod and screw it up into place. And there's 20 of these for each of those support beams. So that's how it works. Now let's look at what happened immediately after it failed. Now this is typically where you begin every failure investigation, regardless of the type of engineering. You start with the physical evidence. And this is often the piece that is done really, really badly. And we can talk about that after. But you're interested in the undisturbed evidence and you go and you take photos of everything. This is from the NTSB report. And it's a photo immediately after the failure. And you can see that the NTSB have gone through and they've labeled all of the key components in this structural system. And you can see the C panels, which are the centerline panels lying on the ground. You can see the end panels lying on top of them. And I do always think this part of a structural investigation is a lot more about common sense than it is about engineering, because you can tell so much about the failure sequence and what happened just by looking at this evidence. If you miss this evidence because you turn up too late and it's been moved, you run into all sorts of problems. So let's have a look at a few of the sort of takeaways from this. Well, straight away, you can see the end panels lying on top of the C panels, and you know immediately about the failure sequence. And that is that the C panels had to have fallen first, and then the end panels fell on top of them. So you haven't done any calculations or any engineering, just applied some common sense, and you've already learned something. The next thing you'll see is that support beam M1 is lying in the rubble. in its entirety. The rods are down there, the plates are down there as well. You can't see it clearly in the photo, but that's all in the rubble, and we'll come back to that in a moment. The other thing you can see is that support beam N is still connected to the roof, and all its hanger rods are still connected to the roots and to the roof, and all the hanger plates are connected as well. So again, without doing any engineering calculations, your evidence is telling you that that beam didn't fail. And if another engineer comes and does calculations that says that beam would have failed or should have failed, well, they're wrong. And this is where the value of this physical evidence becomes really, really powerful. You can shut down so much speculation by experts later on by getting good quality evidence. So that's that first step. What you do then is you slowly remove the evidence. And as you remove it, you keep photographing it, you keep making video of it. You can even do laser scans of it, but you're just trying to capture it layer by layer as it's removed. Then when it's removed, you basically find somewhere where you can lay it all out. And this is where it starts to look a little like the air crash investigators. And what the NTSB have done here is they've put out all those panels on the ground. And again, by looking at this evidence, we can tell a lot about the failure. First thing is that the end panels are largely undamaged. They've come down almost in their entirety. So that's important, because it means that they didn't physically break themselves. The C panels, though, are completely different. If you look at the C panels, you'll see that the bottom edge of the C panels in this photograph is broke off. And it looks like it's broke off in a clear line. And the question is, well, what does that mean? And the answer, honestly, at this point is we don't know what it means, because one of the key things you do in these forensic investigations is you look at damage and you have to ask yourself, is that damage causative? In other words, did it cause the failure? Or was it consequential damage? Did it simply happen as a consequence of something else breaking? Because when these structures fail, they usually damage themselves quite significantly on the way down. And you spend all your time trying to work out whether it's causative or consequential damage. What we're always interested in is what's called the initiating event. We're always interested in the piece that broke first, that then set off the progressive failure from there. So right now, we don't really know whether that damage on the C panels is causative or consequential. So we can park that for the moment. Then we can go and we can look at this row M1 beam. So they've tucked that out of the rubble and they've laid it out between the panels. And when they examined this, they found, yeah, sure, the beam was damaged, but it seemed to have been only damaged on the way down. It had got bashed up, but it was bashed on the way down, as opposed to it failing in situ and causing a problem. Even more importantly, all those diagonal rods and vertical rods that held it in place were all undamaged as well, largely. The hanger plates that were on top of those rods were also undamaged. That was all connected. So suddenly you found that whole structural system holding up the support beams was working properly, and it failed in its entirety, which means that you know at this point that not one piece of that broke, which then caused and initiated the rest of the failure. So, and again, if someone does engineering calculations to prove otherwise, you can prove them wrong because you've got the physical evidence. So if it wasn't that row M1 beam and all its supporting structure, what was it? Well, that points you back to these guys, the epoxy anchors that hold those hanger plates in place up in the roof. And again, by retrieving these and looking at these, you've got a huge amount of insight to what happened in this failure. Now, the first thing I found was, we're looking at 3 of them here. There was 20 of them in total, holding up that main M1 beam. What they found was that 20 of them were fine. And that meant that the anchor itself had not failed. The steel had not tore itself apart in the collapse. So straight away, you know, again, without doing any calculation, that the initiating event wasn't a fracture or a failure in the steel of the anchors. What is much more intriguing in these photos is the epoxy. And you'll see that the NTSB in their photograph have pointed out lots of interesting things in the epoxy. There's yellowed epoxy, fractured epoxy, voided areas. What does that mean? Well, there's a lot of evidence there that suggests that we're dealing with improper installation. Now, what does that mean? Well, one of the big issues with these anchors is that you are depending on the integrity and the honesty of the contractor who's installing them. And the problem is they're tricky, they're hard work to install, and you have to clean out the hole, as we mentioned, really, really carefully for the epoxy to get a good adhesive bind with the concrete, and that's time consuming, and it doesn't always happen. And the problem is that once these epoxy anchors are installed, there's really no way to inspect them to make sure they were installed properly. So this is one of the known issues with them, and this sort of evidence points to installation issues. So of course the question then becomes is, were these the was this the initiating event? In other words, was improper installation the cause of the failure? Well, we're going to cheat and we're going to jump to the end of the investigation. The NTSB found that this wasn't the problem. This wasn't the cause of the collapse. And the way they did it was they went and they actually improperly installed some anchors and they load tested them. And they concluded that yes, there is an impact from improperly installing them. They are not able to hold as much load, so you do weaken them, but you don't weaken them to the extent that they would cause the sort of catastrophic failure that we're seeing in the tunnel. So they were able to rule that out as a cause of failure based on the evidence they had. So if it wasn't the installation that was the issue, what was the problem? Well, very soon after the incident, they went up into that ceiling space, that large ceiling space, and they started to inspect some of the other anchors. And what they found up there shocked them. I reckon this is one of the most confronting sort of engineering pictures you can see as an engineer, but you can see the hanger plates from some of the existing rods in the ceiling, and you can see that while these would have started off their life nice and flush up against that ceiling, it looks like they have gradually began to pull out of the ceiling space. Now, there was over 600 anchors in this particular tunnel, and they found that over 160 of them had measurable displacement. So suddenly this takes this failure, which looks like a localized event, that you've had some ceiling panels collapse, and it now turns it into a system failure. You're now got a systemic issue in your tunnel. There's something wrong with the anchors in not just the section that collapsed, but in the tunnel as a whole. So what is going on here? Well, in engineering terms, what this looks like is creep. So creep occurs in concrete and it also occurs in epoxy. And what creep is that if you take an epoxy and you subject it to what we would say is sustained loading, which of course this is because it has to continuously hold up that ceiling, that epoxy over a period of time will begin essentially to stretch. And that stretch will grow, and that is what we call creep. So when you look at these photographs, this looks like creep. Now, why would we have a creep problem in the tunnel? Well, to investigate that, the NTSB dug into the type of epoxy that was used. They found that the epoxy was supplied by Powers Fasteners. It was a standard set epoxy that was applied. And the good news is that if you want to supply an epoxy to a tunnel, what actually happens is that you have to meet a certain set of standards, and those standards have creep requirements. You have to demonstrate that you have satisfactory creep performance for your product. And this is a pretty typical curve from PowerFast softeners and their standard set epoxy. So what we're looking at here in the graph is you've got displacement in the vertical axis, which is in inches because it's the US. And you've got some tiny numbers there, 0.005 of an inch. And you've got time along the horizontal axis in terms of days, up to 80 days. Now, when you look at that, what actually happens to produce these graphs is the fastener companies go and install the fasteners. They put a sustained loading on them, a prescribed load. They measure the displacement over a period of time, and you get a graph like this. Now, what you can see is that the creep is increasing. The displacement is increasing. Slowly, it's rising. But there's a few things that are really important about this. One, that it's rising at a very, very slow rate, a rate very inconsistent to what we would have needed in the tunnel. The other thing is that the actual magnitude of that, it's less than 0.005 of an inch over 80 days, is within the requirements of the standard. So as far as the standard is concerned, this epoxy had satisfactory creep performance, which then says, well, hang on a minute, looks like creep in the tunnel, but the results suggests that it's not creep because they're satisfactory. What's going on here? Well, there was another sting in the tail, because what the NTSB did was they took some of that epoxy, they scraped it off the anchors that failed, they chemically tested it, they compared it to the standard set epoxy that power fasteners provide. They found it was different. So suddenly, the epoxy that was on the anchors that failed was not this epoxy. There was a different epoxy in the tunnel. So suddenly these creep requirements or these creep results were not particularly relevant to the epoxy we had in the tunnel. So what happened? Well, it's a long and convoluted story, but the NTSB basically figured out that there was a couple of sets of epoxy. There was the standard set epoxy, to which these results related to, and there was a fast set epoxy. And when they chemically tested the fast set epoxy, they found it was identical to what they found on the anchors that had failed. So now they knew the fast set epoxy was in the tunnel. And after some experiments and some digging, they found out that the creep resistance for the fast set epoxy wasn't like it is in this graph. It was more like this. It was dramatically higher. And if you keep going well beyond 80 days and you go to 6 years, which is what we had in the tunnel, you start to get magnitudes of displacement that are consistent with what we actually saw in the tunnel. So at this point, you probably think we've nailed it. We know what caused the failure, but you don't stop there. This looks like the initiating event. It looks like we had creep problem in the epoxy, and that caused the anchors to pull out of the ceiling. But what the NTSB do then is they follow it through. They start and say, right, that's my initiating event. What happens next? Well, they did their calculations and they worked out that if you lose one of these anchors, if it pulls out, that the anchors beside that get overloaded and that they pull out. And then that progressively pulls out all the anchors. So basically, you unzip all those 20 anchors very, very quickly, one after the other in the roof above the M1 beam. Once you do that, that M1 beam starts to fall down as you'd expect. It drags the C panels off the M2 beam. And what happens after this is, as this continues to fall down, the C panels strike the road. And this is why we get that clean break across the bottom of the C panels. So now we know that that's consequential damage as opposed to causative damage. And then you keep going. What actually happens here is those C panels fall on the ground first, and then the end panels fall on top of them. And again, that's consistent with the photos we have in the tunnel immediately after the collapse. And what you have now, without going into a huge amount of engineering details, which the NTSB did in their report and did lots of calculations, what you have is a very straightforward investigation result, a very convincing investigation report, one that just intuitively feels like it's right. And the reason it does is it is evidence driven. The evidence is driving the hypothesis that we find to be correct. It's not a theory-driven investigation. And the interesting thing about when we go to engineering disputes is, particularly in causation disputes, you can find that this doesn't necessarily happen all the time. You don't necessarily get a good evidence-driven investigation. And this is what drives lawyers nuts when they go and engage engineers. It's one of the key things that drives them nuts. And of course, it doesn't always become evident until near the end of the investigation that there isn't a hell of a lot of evidence here to actually build a convincing argument to what happened. And it turns out that this is not an unknown thing. It turns out that this is reasonably well known in particularly forensic circles. So here's some international quotes which basically say that engineers don't really make good investigators, and particularly design engineers, which is what most engineers are. Our core training is in design, and most of us practice as designers. Suddenly, we're not good at being investigators, and the reverse is also true. If you're a good investigator, you tend not to be a really good designer. I would be an appalling designer, and this makes no sense. If you think about this for a moment, it seems to make no sense. Why wouldn't someone who's designed bridges for 30 years be the ideal expert to work out why this bridge fell down? Why wouldn't that be the case? Well, it turns out that when you want to really dig into this all comes down to what designers normally do. And when you go out and you get an expert engineer to be an expert for you and engage them on a matter, they're probably coming with design expertise, and that's where some of the issues comes from. To understand why design expertise causes an issue, we actually need to understand what engineering design is all about. And this is one of the typical sort of descriptions you get for engineering design. Structural engineering design is all about designing something so that it can safely resist the forces that it's going to carry in its life. So the earthquake loads, the wind loads, the load of people inside it, its own self-weight. It has to resist all those loads and be strong enough to resist all the loads. And it has to do so with economy and elegance. So it can't be too expensive and it can't be too ugly. That's what you're striving for in the process of engineering design. The interesting thing is that doesn't tell you a lot about how the process works. That tells you what the process is, but doesn't tell you a lot about how the process works. A lot better description about how the process works is this one. Structural engineering design is the art and science of molding materials we do not fully understand into shapes we cannot precisely analyze to resist forces we cannot accurately predict, all in such a way that the society at large is given no reason to suspect the extent of our ignorance. Now, this is obviously a facetious description of engineering design, but it's pretty close to the mark when it comes to structural engineering. Because if you think about it, if you're a client and you want an engineer to design a building, over there, what you're basically saying to that client, to that engineer is, I want you to design a building that will stand on that ground of which you've got minimal information on. And I want you to take a guess at how hard the wind's going to blow, what sort of earthquake loads you're going to get, what use people are going to put to that building to, which is going to drive the loading that's on each of the floors. You're asking the engineer to guess all those things. And not only are you asking them to guess for now and for next year, you're really asking them to guess and make sure their guess is correct and appropriate for the next 50 years or the next 100 years, depending on the design life of the structure. And how do engineers and designers deal with this guesswork? Well, they deal with it in a very educated fashion. And they do so using a design process. Now, this is a fabulous process, and it's a process that completely copes with all of the guesswork we've just talked about. And this is how it works. You start off as a designer with a set of requirements and constraints. Requirements will be, I want a 40-story building over there, and the constraints will be it has to sit on this ground, the wind speeds are this, and we've only got this much budget to spend. And from there, you got to get to a design solution. And we say a design solution, not their design solution, because there's multiple ways of making that building stand up. And the interesting thing is this is a process of synthesis. It's about synthesizing the solution to match the requirements and the constraints. That means there's not necessarily one right answer and other wrong answers. There's just better answers that meet the requirements and the constraints. And the way you get to those better answers is you use simplifying performance assumptions. So you use assumptions and you use simplified ones. You don't try to the nth degree to work out how everything's going to work. And the reason why you don't is really sensible. One, you can't. So you can't work this out for 50 years. You have to have conservative estimates in there, and that's what we have. And two, you don't want to overly constrain the construction process. So you want the contractor to have some flexibility, and you want to be able to work around changes that need to happen in good construction projects. So you don't want to eat into your conservatism too much. So these simplified performance assumptions are absolutely critical to the design process. And just be aware, we're not saying it's a simplistic process. It's an incredibly complex process, but what it does rely on is these simplified assumptions. What you also rely upon is your design expertise and experience. Now, what is your design expertise and experience? What that really is your knowledge of what is the best practice when it comes to these simplified assumptions, which usually we've codified or we've put in specifications. And you're a design expert because you know those things and you use those things every day. That's what makes you good at your job. If we contrast that to the forensic process, the process of going out and identifying what caused failure, it couldn't be more different. So in a structural sense, you start off with structural failure, you want to identify the cause, and you want to do so based on evidence. And that's the first big difference between the forensic process and the design process. The design process relies on assumptions. The forensic process relies on evidence. And one of the problems that can happen if we mix up that causation and that compliance question is if you go to a design engineer and ask them to do a forensic investigation, it is really, really difficult for them to put aside their assumptions and work with the physical evidence. But what you're actually saying is take all those assumptions you rely upon every day as an engineer and ignore them, or confirm that every one of those is appropriate for this specific situation. And the way you do that is by confirming every one of those with a piece of evidence. That is not something a design engineer does in their day job. So that's the first key difference between these processes. The second key difference is design is a process of synthesis, like we spoke about, but forensics is a process of analysis. It's about finding the one true sequence of technical events that produced the failure. So there usually is one right answer when it comes to purely technical. And when we go to organizational, it gets a little bit more complicated. But when it stays at technical, there's usually one true sequences of events, and that's what you're trying to get. And not only does the forensic engineer use evidence, but they also use their forensic expertise and experience. And we've already spoken about that with the designer. What is the forensic version of that? Well, it's their ability to collect evidence in a forensically sound manner. It's the ability to develop a wide range of hypotheses as to what could have caused the failure. It's the ability to test each of those hypotheses against the physical evidence. So it's a very, very different skill set. And you can see why it's hard to interchange them. You can, if you put a forensic engineer and said, please design something, they would second guess every assumption they would make and they wouldn't get anywhere. And this is where a lot of the issues, as we've said, comes from in engaging experts. Because this is a process of assumption and this is a process of evidence, you got to make sure you ask each engineer to do the appropriate part of the investigation. The design engineer is perfect to answer your compliance question. Did someone design and construct the structure in accordance with the relevant standards or best practice? Why are they really good at that? Well, they're really good at that because they apply that best practice every day in their day job. And then, you know, as you'd already suspect, the forensic engineer is ideal for the causation piece because they apply their expertise in evidence collection and hypothesis development every day as well. That split is one of the key things you can do when you're engaging an engineering expert. You can ask yourself, am I really looking for a compliance investigation here or a causation investigation? And then check the experience of the experts you want to get and make sure they're right for each. Often in investigations, you'll have two engineers, one doing the compliance, one doing the causation. That works very, very well. Sometimes I write individual causation reports that feed into the compliance reports. Sometimes we write joint reports. It just depends on the matter, but it's the separation that's absolutely key. We'll spend some time in a few minutes on an example that will really show how the interplay between compliance and causation and those two engineers works. But before we do, one thing that I think is really important is when it comes to actually preparing a brief of evidence for the expert, what do these experts want? And when it comes to a structural sense, they want really different things. So the compliance engineers doing a compliance check is really after the drawings, the specifications, the standards. They're after what was the best practice that should have been applied in the design of this structure. And they're going to use that to determine, in their view, whether the assumptions that the engineer who was designing the structure made were reasonable or not, whether they were appropriate or not, given the relevant standards. As a forensic engineer in what I do, I'm not interested in those documents at all. All I'm interested in is the physical evidence. I just want to get to site as quick as I can. And I want to get all the photos like you saw the NTSB take, because that evidence is the key and the cornerstone for a good quality forensic investigation. So that's the key pieces of information your experts need in that early stages of an engagement when the process is kicking off. So let's dig into things a little bit more on the forensic process. What is the forensic process? And I think it's easier to start here, and we'll go into the design process a bit as we move through it, but we'll focus on the forensic process first. What is it? It sounds sophisticated, but is it very sophisticated? No, it's not sophisticated. It's basically the scientific method in disguise. And the really interesting thing when you show the forensic process to people involved in the legal sector is they look at it and it just intuitively makes sense to them. In fact, they think that's what the engineer was going to do anyway, but suddenly it's not what the engineer actually does. So you go and you collect all the physical evidence and all the documentary evidence as objectively as you can. You develop a whole range of hypotheses as to what could have caused the failure. You then test each of those hypotheses. How do you do that? Well, you rule them in or rule them out based on the available evidence. By the end of that process, hopefully you'll be down to a cause or causes of failure. You'll have ruled out certain causes as being inconsistent with the evidence that was collected, and you'll have ruled in causes based on their consistency with evidence you've collected. You're after that one through sequence of technical events that caused the failure. What can sometimes happen, and certainly it's happened to us a few times, is you don't get down to one sequence of events. You can have multiple competing hypotheses, both of which are consistent with the evidence. And the issue there usually is one of the key pieces of evidence you actually need to separate those two hypotheses. In other words, to rule one of them out is missing. You see this in a lot of structural investigations, and we can talk about it after if people are interested in. Evidence has a habit of disappearing in these investigations. And if it does, it can lead to a huge amount of speculation to experts later on in the piece, because we're just simply not able to get those hypotheses ruled out. So let's look at the application of this process to another incident. So this is the Minneapolis Bridge in the US, opened in 1967, a very long bridge. We're only looking at the main span of it here over the Mississippi River. This bridge is over half a kilometer long in total, steel construction with a concrete deck slab basically on top of it. By 2007, this was seeing about 140,000 vehicles a day. So it was a pretty critical piece of infrastructure. As we said, opened in 1967, and they had no significant issues with this bridge for 40 years. So it was fine until 2007. And it was the 1st of July, 2007. It was about 6:05 in the evening, so in the middle of rush hour traffic when this happened. The bridge, the main span in its entirety collapsed. There was over 110 cars on the bridge at the time, and they plummeted down into the river. There were 13 fatalities in this incident. So not only was there fatalities, but a key piece of infrastructure was lost as well. So let's step back a bit. You're the lawyers, you're engaging some engineers to go out and do an investigation of what caused this failure. How do you do it? What should these engineers be doing, and what can you watch them doing to make sure that they're conducting a forensically sound causation investigation? Well, you start with your forensic process and you start with your evidence collection piece. Now, the really interesting thing about structural failures is there's 4 and an extra type of evidence you're after, but let's focus on the 4. There's always these 4 types of evidence that you want to collect. And you can actually sit down with your experts after you've engaged them and they start to collect their evidence and say, show me the evidence you've got in these 4 categories. And if they're missing a category, you start to become concerned because they're missing key evidence. So let's step through the 4 categories, and let's do so within the investigation that the National Transportation Safety Board, the NTSB, conducted on the Minneapolis Bridge collapse itself. So the first kind of evidence, type of evidence you're after, is called post-collapse configuration, which is just a fancy name for the mess that you have. So what we have here is exactly the same as in the tunnel. You go and you take all the photos you can of the collapsed structure in as undisturbed state as you can. And then as each piece is removed, you take more photos to see what's beneath them. In this photo, you can see the NTSB has gone through and they've actually labeled all the photos to be able to, or labeled all the elements of the structure to be able to identify where each piece ended up. And the reason why you focus on the post-collapse configuration is exactly the same as the tunnel, because the order in which things collapsed, what piece is lying on top of what other piece, tells you quite a lot about the collapse sequence. And when you know about the collapse sequence, that can be really helpful in determining what the initiating event was, what piece broke first. So that's the post-collapse configuration. Photos, video, laser scanning, lots of options to be able to do that. The second type of evidence you're after is the geometry. You're after the shape of the key pieces in the structure. This is where things can go wrong very quickly in investigation as well. Sometimes you'll see investigators will say, oh, well, I don't need to go to the site. I'll just review the drawings. I'll assume the drawings are correct. And this causes a big problem because one of the causes of failure could be that what was actually constructed in reality doesn't match the drawing. It could be that the structure in real life is different, and that in and of itself could be contributing to the cause of the failure. The only way you know is you go and you measure the key pieces of the structure. What I would always do and advise people to do is get your measuring tape out and take your photos, but then take photos with the measuring tape in the shot. That way, if an expert on the other side says that you've made an error in terms of doing your measurement, you can actually show them the photograph of the measuring tape to rule out those sorts of issues. So you go and you measure up all the key bits of the structure. Now we'll cheat again in this investigation and we'll jump a little bit to the end. Was there an issue with the geometry? Did the contractor who built the bridge actually put in improper sized or incorrectly sized pieces? The answer was no, they didn't. And the NTSB concluded that the bridge as constructed was as designed. So the shapes of everything matched up. So now you've got the post-collapse configuration, you've got the geometry. The next thing you want to know is the materials that's in the bridge. So obviously this bridge is, well, there'll be a certain grade, strength of material, strength of concrete, strength of steel that's going to be specified for the construction of the bridge. Is that what actually ended up in the structure? The only way you know that is you cut samples and remove samples of the concrete, samples of the steel, you go get those tested and you make sure they are as specified in the design. I would always advise to collect many more samples than you actually need because you nearly always have to go back and do extra testing. But in addition to that, if there's a dispute with other experts in the matter as to the results of the test, you can actually give them a piece of the structure and they can go and do their own testing on it as well. So now you know the post-collapse configuration, you know the shape of everything, you know what everything's made of. The last key type of evidence you're after is the loading at the time of the failure. Now, this is always really tricky with bridges. And the reason it's really tricky with bridges is because the load typically is constantly moving on the bridge. So where was the load at the time of the failure? Now, the NTSB did have some security cam footage on the bridge, so that was useful. But the really valuable piece of evidence they got was this bizarre piece of information. So what we're looking at here is a photograph of the bridge that was taken by a member of the public from a commercial flight that happened to fly over the bridge 2.5 hours before the failure. So someone looked at the window of the plane and decided this would make a good photo. This became a really important piece of evidence, and it became a really important piece of evidence because it showed the NTSB where the loading was very close to the time of failure. Now, what you can see when you look in those photos, particularly in the white box, is a number of things. You can see construction equipment. So there was construction works occurring on the bridge at the time of the failure. Everyone knew about this. This was part of a long-running project. So what was happening was they were replacing the wearing course on the bridge. So what that means is you build and construct these bridges and design them so that you've got a concrete deck slab like we talked about. And then you put a 50mm layer of concrete on top of that as a wearing course, because that concrete will wear, as its name suggests. And what you want to do periodically is go back and dig out that wearing course, put in a fresh layer of concrete, and that protects the bridge deck below from wear. And this was progressively happening. So what was happening was a contractor was coming along, picking a section of the bridge, removing a portion of the wearing course and replacing it with new concrete. They were mixing the concrete off a little yard off the side of the bridge. They were bringing it up and placing it on the bridge. And this was working well because the contractor was started on one end of the bridge and they were moving across the bridge. But by the time they got to this point of the project, they realized they had a problem. And the problem was this. The Minnesota Department of Transport had a rule that only 1 hour, a maximum of 1 hour, could elapse between when you mix the concrete and final placement. So you had 1 hour from when you mixed it to get it up through the traffic control, poured into where it needed to go, leveled out, placed. And that worked fine when they were near the edge of the bridge or the end of the bridge, and the travel distance wasn't significant. But as they got across that bridge, that became a real issue. The contractor discovered that they didn't have enough time to get the concrete mixed, transported, and placed within the hour. Now, we could go through a whole other story about what happened here, and it's a bizarre story. But ultimately, to solve this problem, what the contractor decided they do is they decided to mix the concrete on the bridge. Now, to mix the concrete on the bridge, you need all the raw materials to do so. And if you have a look inside that white box, you'll see a gray blob and a brown blob, and you'll see a concrete truck, and that'll give you a sense of scale here. That gray blob is gravel, and the brown blob is sand. The NTSB, from this evidence and other delivery evidence, was able to delivery information to the site in terms of materials, was able to work out that there was over 260 ton of material on the bridge at the time of the failure. Now, if that doesn't, intuitively make sense, or that doesn't ring a bell as to how heavy that is, that's the equivalent of about 1.5 Boeing 747s parked on that bridge. If we want to put it in engineering terms, the load that was on that bridge was 4 times the design load of the bridge. So here we have a bridge that is dramatically overloaded at this point. And at this stage, I suspect you've jumped from the evidence collection phase into the hypothesis development phase, and you reckon this is the smoking gun. But you have to hold off on that for a moment. And that's one of the constant things you have to hold off in a solid forensic process. You have to avoid going to the hypothesis phase, but you get confirmation bias and you see the evidence you want. But certainly you're left with a smoking gun of, is this the cause of the failure? Is there so much load on this bridge that it collapsed the bridge? But the key thing here is there's 4 types of evidence you're after: post-collapse configuration, geometry, material properties, and loading at the time of failure. If you engage an expert to do a causation investigation, you should be able to sit down with them and say, show me the evidence in those 4 categories. Now, there's a 5th type of evidence, which I mentioned, which I would class other. And I know it feels like a bit of a cop-out to say there's other evidence, but there always is an investigation. There's other evidence that becomes important, and it's nearly always different from failure to failure. The key other evidence they found on this particular bridge was that at the same time as a causation investigation was going on, there was also a compliance investigation going on. So there was a group of engineers working out whether the bridge was designed and constructed properly with respect to the relevant requirements. What they found out was, no, it wasn't. There was some issues with the bridge, and they found that some of the connections of the bridge, 4 on this side, which I've highlighted, and 4 on the other side, were deficient. They didn't meet the requirements. And what was the issue with them? Well, the issue was that you've got these members coming together, this upper chord, the vertical, and the diagonals, and you've got to connect them. And the way they connect them is with a flat piece of steel called a gusset plate. And in this case, all those members are riveted into the gusset plate. If this bridge had been designed according to the relevant standards, that gusset plate should have been 24 millimeters thick, so about 1 inch thick. They found in the design drawings and in the geometry on the bridge was that some of those gusset plates were half that. They were only 12 millimeters thick. And that's a huge decrease in strength from a structural engineering perspective. They were way thinner than they should have been. Now, so we know now we've got a design issue in the bridge, we've got a compliance issue in the bridge. But this is really important. And we see this in a lot of engagements. We see engineers that say the bridge wasn't designed properly, therefore that's why it fell down. But they then don't do the forensic link to join the compliance issue with the actual failure. And the reality is you can have lots of compliance failures in a structure, but it won't lead to its collapse. The proof of that here is this bridge had a serious compliance issue, but it still survived for 40 years. So that doesn't mean it necessarily was causative in the collapse. So hold that thought for a moment. But what we can ask ourselves is, was there any distress? We know we have this design issue, but did we see any physical distress in the bridge? And it would turn out that, yes, they did. That there was a range of work done on the bridge by the company called URS and by the Minnesota Department of Transport. And over the years, they'd done some strain gauging, which is a form of measurement on the bridge. And like all engineers, they went and took lots of photos of the bridge. And this is one of the photos of the critical gussets that was under designed. And you can see, if we zoom in a little, that there's a significant bow in that gusset plate. That gusset plate is bending out. Now, in structural engineering, this is really bad. You do not want things that are getting squashed, which this gusset plate is, to bow. The minute something bows, it's already losing strength. So you imagine you take a ruler in between your hands and you try and push that ruler is really, really stiff, really, really hard to push. But the moment that ruler bows, it's really, really easy to push that ruler in and out. And it's the same in structure. So a lot of structural engineering in steel is designed to stop the bowing ever even happening. Because you know, once it's bowing, you're in a world of trouble. And this evidence shows that these gusset plates were in a world of trouble, and they had photos for all of the gusset plates. And you probably can't read the date down there on the bottom, but remember that the collapse was in 2007. This photo dates from 2003. They also have photos from 1999. So like all structural failures, you tend to see, with the benefit of hindsight, lots of warning signs that failure was coming. So that's the evidence collection piece, your 4 key types and other, and always make sure they're. The key thing with hypothesis development is to develop a whole range of hypotheses. In this particular case, we're going to focus on one. We're going to focus on the hypothesis, which is, did that huge loading on the bridge due to the construction loading cause the collapse? And did it cause the collapse in combination with the presence of the design error? So that's the hypothesis we're interested in testing. How do you test that hypothesis? Well, like a lot of structural engineering and mechanical engineering testing, you build a computer model. You build a virtual model, sometimes called a finite element model. There's lots of different names for them. And this virtual model, you can subject to the loading that the real bridge was in real life. Now, if you're a lawyer and you've worked with engineers building these models, they're a nightmare for the legal fraternity, because it's real black box. It's really hard to see what's happening in that black box and convince yourself that the engineer has got it right. And many times we see huge problems with these models. Whenever you see these models, I would ask you to remember my favorite quote about computers: that computers have enabled people to make more mistakes faster than almost any invention in history, with the possible exception of tequila and handguns. So please treat these models with a lot of skepticism even. And how do you do that if you don't know anything about finite element modeling? Well, the way you do it is you focus on the inputs to the model and the outputs to the model, and you make sure the inputs and the outputs are consistent with evidence. And you can do that because you've gone and collected all the evidence. So here's a model that was built as part of the NTSB investigation. We're zoomed in on one of those critical joints. This was part of a much larger model. And how do you build this model? Well, you go and you put in all the geometry of the real bridge. How do you know you've got that right? Well, you check it against the physical geometry that you went out at the site and you measured. You put in the material properties of the materials in the bridge into the model. How do you know you've got that right? Well, you know you've got that right because you went out and you did some testing and you collected them and tested them. Then you apply the loading to the model. And how do you know you got that right? Because you went and you collected your evidence for that as well. So you are using an evidence-based approach to confirm the model is as good as it can be. Sit down with your engineers, with their models, and say, show me all your assumptions and show me how you made sure they're consistent with the evidence we've collected. The NTSB built the model, they run the model, and they demonstrate that as that loading is applied to it, what actually happens to this model is that whole joint kicks over to the side. You get a lateral shift in the model. You get those red areas in the gusset plates, which are the really highly stressed areas, which means they're going to fail first. And that joint basically tears itself apart. Once you tear that joint apart, the rest of the structure progressively collapses. You don't stop the model running, you keep the model running, and you make sure that the manner in which the model collapses is the same as the way the structure collapsed in real life. And you know that because you went out and you collected all the post-collapse configurations. So that's the other piece you check with your experts. Is their model giving a collapse sequence that is mirrored by reality? If it's inconsistent with the photos you've taken, then it's wrong. And it's back to the drawing board to understand why it's wrong. The NTSB didn't stop there though. So they did all that, but then they said, right, our gusset plate is our initiating event. That's the key thing we're interested in here. And they sent the divers down into the Mississippi to actually go and fish out these gusset plates from the bottom of the river. This is one of them they pulled out. You can see they have tore themselves apart, and they basically built jigsaw puzzles. So this is as they put them back together again. The blue lines are where they physically tore themselves apart. And then you compare this with the model. And when you compare this with the model, you'll see that by and large, the blue lines where the plates actually tore themselves apart, is very consistent with the most highly stressed areas in the model. So this gives you more comfort and proof that your model is giving you the right answer and that you're on to a forensically sound investigation. And that's what they found. They were able to rule out all the other causes of failure against the evidence they have, and they concluded that the cause of failure was the loading on the bridge at the time of the failure in combination with the design error in the bridge. Now, this is really interesting. This is where you get to the interplay between the causation engineer and the compliance engineer. How do we know that it's both of those? How do we know we need both of those to cause the failure? Well, the way to think about this is, we've got a massive load on the bridge. It's 4 times the design load of the bridge. Maybe even if the gusset plates were designed properly and constructed properly, maybe that loading was so bad it would have collapsed it anyway. And if that's the case, then the physical cause of failure is just the loading. It's not the design error. Well, how do you test that? Well, this is where you get the interplay between the causation and compliance. You can say, and I've done this in many investigations, you can say that the compliance engineer, what should it have looked like? In this case, it should have been twice as thick. You can go to your model, which is what the NTSB did. They made it twice as thick in the model. They reran the model, and they found in that case that even though you had this excessive load on the bridge, the presence of that load alone was not enough to collapse the bridge. That means you needed that loading in combination with the presence of the design error to result in the collapse. And that's where the interplay and causation of causation and compliance works really well. So in summary, the key takeaway here is there are many different types of engineers. And I think we as engineers are only catching up on this. The legal fraternity is very comfortable with the concept of accountants and forensic accountants. And they do very, very different things, and you probably shouldn't mix them up. It's the same when it comes to engineering. You have design engineers, forensic engineers. I like this split. The design engineer is obsessed with what should have happened, and the forensic engineer is obsessed with what actually happened. Because when you find out what should have happened, you're really answering the compliance question. When you find out what actually happened, you're identifying the cause of failure. And just to close the loop on the briefing material these engineers lead, the design engineer wants the design documents, and the forensic engineer wants physical evidence. I will leave it there, but if you're interested in more about forensics and design and the cause of failure, we have a podcast, which Jodie's probably going to mention, called the Brady Haywood Podcast. You can get it on iTunes and all your usual places, and it covers the same sort of stuff as we've covered this evening.
Thanks, Sean. That's fantastic. We've got a couple of questions, if you don't mind. The first one is from Ian Ferguson, and he thanks you for a great presentation and asks, how do you think the process would vary when you're investigating a failure in asset maintenance, if at all?
Yeah, well, the reality is they're sort of interlinked, because you've got the design and construction of the structure, but if the structure is old, particularly like the bridge was and the tunnel was, you got to take into account the asset management of it as well, how it was maintained, and you get into that forensic design split there as well. You get into, well, did the lack of maintenance cause the failure? That's the forensic side of that. Whereas you've also got the compliance side, which is how often should it have been maintained. Interesting story with the bridge. The bridge had to have regular inspections, and they were quite proud in the Minnesota Department of Transport because they were actually inspecting it more regularly than they needed to. So from a compliance perspective, they were doing a good job on regularity, but they were missing the fact that they were getting the bowing in the plates. Different story with the tunnel. The tunnel is interesting because that should have been inspected around 2003. So it went in 2000, should have been inspected in 2003, collapsed in 2006. The NTSB held the view that if it had been inspected in 2003, they would have saw those anchors pulling out of the ceiling. That would have been a pretty confronting thing to find. But somehow, from a maintenance and inspection perspective, that tunnel was never inspected. So yeah, you got to take it into account in the investigation.
Great stuff. We've also got a question from Jordan Bartlett, who says it's a non-legal mind asking. Don't worry about that, Jordan. The interplay of two outcomes is fine. Can forensic engineers assist parties to assign percentage culpability?
Oh, that's a really tricky question. Just exactly what I'd expect from you, Jordan. And that's a compliment. It's really hard. I mean, at the end of the day, I avoid getting into all of that because there is lots of legal mechanisms for dealing with that. What I'm after is that one true sequence of physical events that produce the failure, and then you let the lawyers work out how to assign blame from that point forward. We're only here as forensic engineers to say this is what happened. Now take it from here.
And last question from Graham Vile. Do you think we do enough about sharing engineering failures in Australia?
No, we're terrible. We're absolutely terrible. To be fair, most professions are terrible, and we've come a long way. One of the key things that has happened in the UK and Australia is the formation of it used to be called SCOS and CROSS, now it's called structural safety, and it is all about sharing the lessons of these incidents back into the profession. So if you're not familiar with it, I encourage you to go and look it up. It's really good. It's the best we have. We suffer from the issue of that when a failure happens, it usually becomes a legal dispute. Everyone gets caught up in confidentiality very, very quickly, and those lessons don't get disseminated. I would suggest that if there was a similar thing in the airline industry, that would be publicly unacceptable. When we crash a plane, the community feels it has a right to understand what happened there and feels there is a need to investigate that publicly. We don't always have that in forensic investigations. A lot of the presentations I do are structures in the public domain, and they're really always bridges, because when bridges fall down, there is a very public examination of why they fell down. With building failures, there is not always a good public examination and presentation of why they fell down.
Which makes it difficult for the whole industry to improve. There's a great question from Manji Shabadia. How can we incentivize people to share lessons of failure to learn from them?
It's really hard. And every profession struggles to do this. Nobody wants to tell the bad news. I mean, I always say, you can pick your favorite engineering firm that and they'll do a big project, and then they'll go and do a big presentation about how successful and how difficult and how everything was overcome to produce this great project. That is a really valuable thing to do. But could you imagine if you had a project that went wrong and you had companies willing to stand up and talk about just why it went wrong, what their role was in it going wrong, what they know, what they don't know. We as a profession would learn a whole lot more, but that is a very, very difficult thing to do in the modern world. But if we can do that, that's what we need to try and get to.
Great stuff. Well, we might leave it there. We've got no more questions, and we've definitely hit time. So thanks, Sean. That was really informative. We'll follow up this webinar with a handy summary article to all of the participants. So thanks very much for coming. And that'll include some key information from today's presentation. And meanwhile, you can find us at bradyhayward.com.au, and we're on LinkedIn. And just like you spoke about before, tune into the really popular Brady Hayward podcast series to hear more about the causes of engineering failures. On behalf of the Brady Hayward team, I want to thank you for joining us today. Thanks to you, Sean, and also to Laura for in the background making everything work, and also to all of our participants. It's been really great to have you. Have a fantastic day. Stay well.